This is the solution video for Exam 1, Problem 4. And in this problem we will be designing a comparator that can take some consideration whether or not the numbers are both odd or both not odd, or not both odd. So here, this is one or the other can be even, or both can be even, and this is they're both odd. So the first part of this question asks you to kind of parse this. So this is part A, and this is really part B, or sorry, part C. So describe in English how you determine P0 and Q0. So what I know is I want to start off with the assumption that they are equal. So that's when I have this or this. So that's when Q is 1, is when they're equal. So I want the first comparator to assume, comparator cell, to assume that A and B are equal. So Q0 should equal 1. And then I want, the next thing is I need to figure out the odd even part. And so I will check for both odd by basically if they're both odd, A0 and B0 should both be 1, anding A0 and B0 by ANDing A0 and B0, A0 and B0 are 1 when A and B are odd, respectively. Both odd by ANDing A0 and B0, A and B are 1 when A and B are odd. Okay, good. And so then I need, basically it's P0. P is 0 when they're odd, both odd, and so then NANDing and then nodding the AND to find P0. So based on my answer to here, this is basically saying Q0 is equal to 1, and P0 is, both are odd, so that's A0, B0, but I want P to be 0 when they're both odd. So that's the complement. Essentially, this was a cleverly disguised solution strategy. That's really all there was to that. So that's that, and based off of this, I have B, and now I can go on to designing the cells of the comparator. So the first thing you should hopefully notice about this whole thing is that P is 0 whenever they're odd, and P is 1 whenever they're not both odd. And doesn't really affect whether or not A is greater or less than B. So this actually, the P bit doesn't contain any information about greater than or less than. It only contains information about odd or not odd. And so really, it's actually just going to stay consistent throughout the entire thing. So, because after the first bit, you can't change whether or not it's odd or even. It's done. So P sub I plus 1 is going to equal P sub I, because we can't change the odd-even relationships. So Q is 0 when A is less than B, and 1 when A is greater than B. So another way to think about this, Q equals 0 if A is less than B, Q sub I plus 1, and Q sub I plus 1 if A is greater than or equal to b. So I only need to write a 3 by 1 truth table with q sub I, 0, 1. And then I'm going to have a sub I, b sub I, 0, 0, 0, 1, 1, 1, 1, 0. And I shall output q sub I plus 1. So this is less than, and this is greater than or equal to. And so if I knew that they're less, a is less than b earlier, the most significant bits are the same. It's going to stay less than, so that's going to be 0. Then we have a is less than b, the most significant bit. A is less than b. Here we've got the equal again, so that's going to stay the same. And then we've got the most significant bit of a is greater than the most significant bit of b. So that's going to change it to greater than or equal, so that's 1. So here we can think that 0, 0 is greater than or equal. Either way, it's going to stay greater than or equal with this 0, 0. So this is going to stay a 1. And then here we've got, oh, look, it's 0, 1. So a is now less than b because the most significant bits, so that becomes 0. Greater than or equal to will stay greater than or equal to at this point, with them being the same, and greater than or equal to will stay greater than or equal to if they're greater than. And so for minimal, there's not really a great solution for this, so we're going to have that, that, and that. And so q sub I plus 1 is going to equal q sub I, b sub I bar, so that's that one. And then we're going to have q sub I, a sub I, that covers that, or a sub I, b sub I bar. And that completes problem 4.